Let's price options using the Heston model in C++. Professor Steve Heston went a step beyond Black and Scholes for option pricing. In the early 90s, he proposed a model where not only the price of the underlying follows a random path, but also the volatility does. Instead of using some static measurement like Black and Scholes, his model assumes that the volatility reverts to its mean, but follows a stochastic process as well. But how can you implement this in C++ in an efficient way? Well, before that, let's take a look at the model itself. The price of the asset is determined by the following stochastic process. If you've worked with Black Scholes, this looks familiar, right? This basically says that the change in price of the underlying is determined by the previous price, some volatility, and a random term represented by this Wiener process. The caveat here is volatility follows this process that is also random, and the two random terms have a correlation. To calculate this correlation, we'll use the following formula. Alright, enough talking, let's look at the implementation. For this example, we'll price an at-the-money call option with the following parameters, and we'll just print the option price at the end calling a function with all these parameters. Since we'll be using random observations from a normal distribution, we need to initialize the random generation engine outside of the function, since this is a really heavy process and we don't want to deal with it every time we call the function. Alright, and for the function itself, let's take a look at the steps. By the way, notice that simple data types are passed by value, but every object we can pass as a reference, we should do so to avoid memory copies. If the object doesn't change, it's even better to use a const reference. For the model itself, we need to discretize time to be able to get our time delta. We'll also need rho squared to calculate the Wiener process correlations. After that, let's initialize a vector to store the payoffs. Instead of using the constructor, reserve memory for it. Check out my video about vectors in C++ if you want to know more about this. Now, for every simulation we've defined, let's initialize the price as the initial price and the volatility as the initial volatility, and let's do a random walk for every time step n that we've defined. So, in every step of the random walk, we'll get two observations from a normal distribution, and we will define the first Wiener process as the first observation, and the second one follows the formula of the correlated Wiener process. This is what we calculated the rho squared for, and it's essential for performance that we calculated it outside the loop, since it's always the same. Now, to update the volatility, we'll use this little discretization trick called the Euler-Murayama method. And of course, we can't have a negative volatility, so we'll use studmax to limit it down to 0. We'll also discretize the price, and the resulting equation looks like this. So this is the resulting code. When every simulation finishes, we store the result in the payoffs vector using a core option price formula. And we are done simulating. Now we simply take the average of the payoffs and discount it with the risk-free rate, and we have ourselves a price. Let's look at the output. This is more stable the more time steps and number of simulations you use, but take into account there's a trade-off between time and precision. Now that you know how to implement the Heston model, go play with it and take your own conclusions. If you want to know how to price an option using a different method, like our binomial tree, go watch this video. But for now, I'll see you in the next one.